Hey y'all! Well, when I posted these recent videos about the 12AX7 EL34 build, got a lot of comments. Thanks for the, constructive criticism and ideas and stuff. But a couple of things I need to explain about why we can't do certain things. Like, one of the viewers was saying, I don't understand why people don't design amps around 12 AT7 tubes, because they're cheap on eBay, they're easy to get, they got all these new old stock ones for peanuts everywhere, and it was almost like it was a conspiracy that we don't design amps to use those tubes because we want people spending money on these other ones. And that's just not what's going on here. Also, somebody asked about a couple of other tube types, if they think that it could be either, a plug-in replacement for the 12AX7, or if they could, put in an octal socket and use like a 6SL7 instead. And we're fixing to dive into load lines and tube curves and, all this fun stuff that helps you figure out what'll work, what won't, etc. And yeah, the other one was a 5751. So without giving a spoiler away, let's dive into designing the front end of a tube amp, how you can do this yourself or learn to do it, what load lines are, how to draw them up, how to figure out the bias points, and what happens when you're playing around with that bias point. So anyway, I thought this was a good time to do an educational video on this. For a couple of years now, people have been sending me emails, when are you going to do a video about drawing load lines? Well, today's the day. Let's dive into it. Okay, so the first thing we need to do is look at the circuit that we're going to be working with this 12AX7 tube. And yeah, you're probably overwhelmed looking at like all of this stuff on here. Well, today we're going to be focusing on the driver tube and how to draw load lines for it and evaluate how it's going to work. And so we don't need to be bothered with any of this over here, because we're just looking at the driver tube. And actually, this stuff over here isn't important either. This volume potentiometer, that's not part of what we're doing today either. So all we're worried about is this is going to the output tube grid, and we're just looking at this part of the circuit here. And really, this isn't even important. All that matters is we've got 405 volts coming in here. Then we got this 240K resistor. So when we're drawing a load line, we need to pretend like that this tube is capable of doing things that in reality it can't. On one end of the scale, we're going to assume that the tube is turned off completely and there's no current flowing across it, because the measurement that we're going to be taking here is on the plate. So if the tube is turned off and there's nothing conducting across it, we're going to have no voltage drop across this 240K resistor, and so we're going to have 405 volts sitting here on the plate. The other end of the line is going to assume is the tube is 100% conducting, which means these two wires are connected together, and that we're going to have 0 voltage here. So in that case, we have 405 volts across this resistor, and how many milliamps of current is going to be flowing through this resistor with this wire shorted to ground. So let's go calculate up those two things. And I'm not going to bother showing y'all the math, because this is what I use ohmslawcalculator.com. Makes it simple. It calculates up the voltage, current, resistance, and the power. So if you need to know like wattage, it calculates that up for you. And then you can set these for milliamps. You can set this for kilo ohms. And so we have 405 volts. And then the other known thing is we got 240K of resistance. And we've got, let's just round this up to 1.7 milliamps. So we got 405 volts as one of our measurements, and the other one is 1.7 milliamps. And those are the two things that you need to know. So going back to this other screen, okay, one of the key things to note here is this 510K of resistance that's going from the other side of the coupling capacitor to ground. Just let's forget about this resistor for right now. It's inconsequential. Doesn't matter. What matters is this 510K. And so that's the load that this tube is going to see. Now the grid could have a little bit of capacitance and stuff, but for what we're doing, don't need to really focus on that. So we're just going to kind of ignore that part of the equation. And this is the grid leak resistor for the output tube. So how did we come up with this 510K? We got it from the EL34 datasheet. The key thing that we need off of this datasheet is this right here, which is the resistance of grid 1, which is the control grid, to the cathode. The maximum that it allows is 500K. And we fudged by 10K, which I'm comfortable with. That's where we got this 510K resistance, is from this data sheet. And there isn't a common value of 500K in a resistor. You can use either 470K or 510K. Honestly, it's not going to make really any difference. If you feel safer, you can use 470K. I've been using 510K, hasn't been a problem. So that's where the 510K that we see here is. That's the maximum grid leak resistance that we can have with an EL34 tube. And other tubes like a KT88, a KT120, they have different values of this, which contributes to some of those tubes being harder to drive. EL34 tubes, easy to drive because it's got this fairly high grid leak resistance. So now that we know that, let's go look at the 12AX7 datasheet. So here's the datasheet on the 12AX7. Here's where it shows the pinout. It shows the heater voltages, the heater current. We're going to be using it as a 6.3 volt parallel. That means that pin 9, which is the center tap for the heater, is one side of the heater winding, and then you tie pins 4 and 5 together, and that parallels the heaters where we can run them at 6.3 volts. The other thing to note is saying the maximum volts on the plate is 300 volts, and that's like the voltage on the plate, not the voltage feeding the plate load resistor, which we will get into. So heater to cathode voltage isn't a concern because we're going to be running about 1.5 volts on the cathode or 1.8 volts, but you need to watch this too in certain applications that this doesn't exceed this value or the cathode will short to the heater. And then the other thing is the plate dissipation is 1 watt. So if we look at the characteristics and typical operation, it's a Class A amplifier, which is what we're doing. For a plate voltage of 250 volts, they're saying about negative 2 volts on the grid. We got an amplification factor of 100. And then here's the plate current that we're looking to see, something close to that, is 1.2 milliamps. So let's look at this chart. And this isn't in all data sheets. You only find this on the older data sheets, but this is a very useful little chart, and it helps you set up the tube. And I think they did this a long time ago because they knew more hobbyists were working with tubes. And if you look at any of the current tube data sheets, they're super abbreviated. Most of them don't even have the curve charts or any of that stuff. They just have, the basic kind of information like we saw on this page. So back to this little chart. First thing we want to look at is this RS. And I hope this looks familiar. This is the coupling capacitor, and this is the grid leak resistor for the EL34 tube, which is 510K. So come over here to this chart, look at RS, and there's our 510K, which if you used a 470K, it would be, very similar. So we know we're going to be using this line here because on this RP, we're using 240K, which is this line right here. And it's saying that the grid leak resistor should be 100K, which is we're using a 100K pot, so we're good. Probably could be up to a meg and it really wouldn't be a problem. So we come over here and we look at this last line here, and it's telling us the cathode resistor, if we were using a cathode resistor with a bypass cap, would be about 1800 ohms. And that would get us where we want to be as far as the cathode voltage to the grid voltage. But we're going to be using a different setup with an LED plus a resistor. But I just wanted to point out this chart, that this really is helpful if you're starting from scratch, trying to figure out hey, where does this thing kind of need to be? And this is very helpful, and like I said, you can find this in the old tube data charts. So this is what we're really interested in dealing with today, and this is the curves of the tube that shows how linear the tube operates and allows us to pick a bias point. So let's open this up in Photoshop. Okay, so we've got the 12AX7 curve characteristics, or plate characteristics as they call it, opened up in Photoshop so we can draw on this thing a little bit. So remember that when we calculated the 405 volts across the 240K resistor, we had 1.7 milliamps. So we're going to put a mark up here in the plate milliamps at 1.7 or approximately thereof. And then we're going to come over here, just go just a breath past 400, and that's our load line. And again, the endpoints of this, 0 volts. That's assuming that the tube can actually short to 0 ohms, and you'd have 0 volts on the plate. You'd have 1.7 milliamps across the plate load resistor. And then if the current was 0, which means the tube is totally turned off, then you'd have 405 volts on the plate connection. And again, this is theoretical. The tube can't go dead short, and the tube can't completely turn off, but this is how you draw the load line. So we know from looking at the schematic that we've got 1.8 volts as our bias point. We've got a 1.6 volt LED, and then if we do the math to get 0.2 volts, we're going to have 160 ohms. So again, we know on this schematic we're looking for around 1.8 volts here on the cathode, which is the 1.6 volts from the LED. There might be 1.55 volts in actual use, and then we've got this 160 ohm resistor, which we can adjust the value of this to get our bias point dialed in. So we're back to our load line, and we're going to draw a line here at 1.8 volts. And this is our bias point. So while we're drawing this, we're going to assume that we're going to have about a 2 volt peak to peak voltage swing on the input signal. So we're going to come up here to 0.8 volts and draw a line, and then we're going to come down here to 2.8 volts and draw another line. This is our voltage swing that we're going to be seeing across the input signal, and how that relates to the voltage swing that we're going to be seeing on the plate of the input tube. So when it gets pulled down to 0.8 volts, the plate is going to come down here to just under 150 volts. I think that's 150 volts right there. These grid lines are really hard to read on these old charts, but going to have probably about 140 volts. And then on the top end, you're going to have about 280 volts. So we're going to have about 140 volts swing on the plate from 2 volts of swing on the grid of the input tube. So that's where we get our amplification from. And the main thing to note here is this area where these lines cross. As the signal strength changes, the gaps between these lines are really even. Now if we had it down here lower, where it was going across this part down here, you'd end up with problems with the lines on one end being a lot closer together than the other. And I'll show you some other tubes that have curves that really aren't linear, like a 12AX7. And it's why this tube's used so much in audio, is that these lines are very evenly spaced, and it is a very linear tube, especially when you're operating it in this zone right here. Now, we may end up with 3 volts peak to peak on the input signal. And in that case, you're going to end up with like 1.5 volts from here. So you're going to end up with like 0.3 volts. And then you'd end up with 3.3 volts. You can see we're still in a really nice linear part of the tube, but we're starting to crowd this line down here versus this line. So it's probably going to be a little more distorted if you overdrive it this much, but it's still not problematic. The other thing you have to be aware of is you do not want to drive the grid positive. That's why they don't have any lines up here, is you need to keep the grid negative. And so that's why we've pushed this a little further down this boundary. Instead of being up here at 1.6 volts or 1.5 volts, we want to be closer to this 1.8 volts. So we've got some headroom here between the bias point and 0 volts on the grid. In case we have a hot signal coming in, we're not driving the grid positive. So I hope that makes sense. So let's go ahead and look at a couple of other curved charts. Okay, here's the 6SQ7, which is the first version of this amp. Again, if we go up here to 1.7 and just over 400, our load line looks like this. If we come in here at 1.8 and then at 0.8 and then at 2.8, again, you can see along this load line how evenly spaced these curve lines are, which is going to give it a very linear sound with low distortion. And again, on this tube, if you go down to 0.3, you're still fairly linear, but again, once you start overdriving these tubes, you start getting into a more distorted area where you can see the gap between this line and this line is not as wide as the gap between this line and this line. So we really want to keep the tube in this happy zone right in here. Now, supposedly the 6SQ7 tube can handle a little bit of positive grid voltage, So you possibly could bias this a little lower and get it in a more linear area, but I didn't want to push that envelope, so that's why I biased it here. And actually, from playing with it, it sounded best biased there. So another tube someone asked about was the 5751. So let's take a look at it. So again, we're going to come up here to 1.7 milliamps over here at 400. And like the angle of this line's different, but you can see the relative voltages is going to stay about the same on these tubes that we're looking at. There's 1.8, there's 0.8, there's 2.8, and you can see the gap between here and here is the same. And if you look along this line here, the gaps between these lines is the same as well. And we're ending up with a very similar bias point with this tube as well. And so I think you should be able to drop this 5751 tube into this amp without any problems. The other thing somebody asked is, can I use a 6SL7 with this amp because I like octal tubes? Well, let's take a look at what the load line looks like using a 6SL7. And we go in here and put our bias point, 1.8, and that's approximately about 0.8, and there's 2.8. Again, you see the gap between here and here, here and here is even. The lines are really evenly spaced along this point of the curve, and so you should be able to use a 6SL7 for the driver tube in the same circuit, just changing the tube socket and obviously doing the pinout wiring different. So that's the load line. That's how you calculate these things up. And then somebody else asked, why can't you use a 12AT7? They're really cheap on eBay, and you can find them everywhere. They're a whole lot cheaper than a 12AX7. So let's look at why they're cheaper. You guys seeing what I'm seeing here? Look how different the spacing is between the different lines on this curve chart. It's just not even the same sport. And if we're trying to do what we were doing with those other tubes, it's not going to work. This is pulling a lot more milliamps of current than the 12AX7 is. And if we look at the 12AT7 data, here's what they're saying to use at 250 volts. You're going to have negative 12 volts on the grid instead of negative 2 volts. You're going to be pulling 10 milliamps across the tube instead of 1.2 milliamps. And it's just completely set up different. And the comment was, well, I know the amplification factor is a little lower, but I don't really care. The problem is it's just a totally different kind of tube. And while you could go through some gymnastics and try to make this tube work, there's a reason why 12AT7 tubes aren't used in many audio products. It's just not ideal. So again, let's look at the 12AX7 tube data, and we're going to be running it at 250 volts, the same as that, right? We're going to have 1.2 milliamps and negative 2 volts. We're on this one, we're going to have 10 milliamps and negative 12 volts. It's just, it's not even the same. You can't just drop them in and expect it to work. It's more than just this amplification factor thing that we're seeing here. So I wanted to kind of go over that too. And the last thing that you need to do to ensure that tubes are compatible, here's the pinout on a 12AX7. Center tap for the filaments. Got those two at the other end of the filaments. Then you got cathode grid plate. cathode grid plate. So let's look at this 5751. Same thing. This is the center tap of the heater. Those are the other ends of the heater. And then you have cathode grid plate. And then you have cathode grid plate. So tube's got the same pin out. Need to make sure that the pin outs are the same before you start swapping tubes in an amp. Because if the pin out's different, you're putting like plate voltage on the heater or some other crazy thing, you'll definitely just blow the tube up. So I hope that helps kind of explain what's going on. And again, this tube, I'm not interested in trying to make this work in an audio amplifier. I just don't think it's an ideal tube for working in a tube amp. So we can scroll back here through the different tubes that we've looked at. You can see there's the 6SL7, there's the 5751. These have a very similar amplification factor, and you can see down here they're both operating kind of in this lower range of the plate voltage compared to what we're going to see with these other higher amplification tubes. When you get to the 100 amplification tubes, you're working more in this range of 150 volts to close to 300 volts. And the same thing here, 150 volts to 300-ish volts. And again, remember that the maximum plate voltage is 300. I'm not too concerned about us going a breath past it if we're really overdriving the tube. But in normal listening, it's never going to see past 300 volts. And so it's going to be a happy tube. So I hope that helps you understand what load lines are all about. And I think this is a good place to wrap up this video. Well, I hope you found this video educational. You probably can imagine how many hours it took putting this video together on scanning these sheets and doing screenshots and photoshopping these things so that it'd be easy to see in a video format. Just felt it was very important to do this visually. And again, spent most of the day today putting this video together. But it's one of the reasons I've been putting off doing it is I knew it was going to be a lot of work. So, hope you learned something from it. If you did, thanks for joining my Patreon. Thanks for the donations at my website. That really helps me get inspired to spend the time that it takes to make videos like this for you guys. Thanks to all you subscribers. Please subscribe if you haven't. Please like the video. And we'll see you at the next video. Have a nice day.